right then, section 2.2 is going to work with the frequency distributions. And we kind of started mentioning those last time as far as what's going on with them. It is just a way to organize a whole lot of data. If we were talking about ages of students, I would not want to go through and list student ages as 16, 17, 18, 19, 20, 21, and go all the way up until we got to our oldest student and look at how many in every single age we had, because pulling all that data, that's just too many pieces of information that it still would not, it still would not help us out really well. Instead, we're going to group ages of, 0 to 18, 19 to 36, or whatever. We'll group them in certain groups to be able to see how many fall into each of those different categories. That's when you're talking about your frequency distribution. So it's when you're working with those large data sets, it's often helpful to organize and summarize the data by constructing a table called that frequency distribution. It helps us understand the nature of the distribution of a data set. And so last time we went through several of these terms, didn't we? We did get started. We talked about what that frequency distribution looked like. We talked about the lower class limits and the upper class limits being the smallest and largest numbers you can have. The class boundaries are, it butts up against each other, and there is no space between things when you're talking about that boundary. The boundaries are usually numbers that are not physically possible, but it's telling you where that middle of that spread is, and it's giving you, so if we were talking about ages, if you were doing 10 to 19 and then you did 20 to 29, then the boundary would be at 19.5. Again, not an age that you'd be categorizing, but it's still saying that that is where it would split. So everybody would either be 19 or it would be 20. You're never going to have that 19.5 when you're talking about those boundaries or things you're not going to see. Your class midpoint is finding that middle value by finding the average between your lower and upper limits. Your class width is the difference between the two consecutive lower limits or lower boundaries. And so I want to look at an example. And let me find my example. That's not my example. There it is. If you look at page 48, looking at page 48 kind of helps step us through what's going on as we look at these. And I have an example on this grocery list. And I know seeing the numbers is tough to see, and I'm not even going to be able to show all of them to you at once. But looking at what's happening, this is spending amount in dollars. This is finding the amount spent in a grocery store by 50 consecutive shoppers. So not a good, simple, random sample since they just took the next 50 people that came in. But and they put them in order. One person spent $2.32, another one spent $6.61, another one spent $6.90. The one that spent the most was $69.49. I definitely didn't go grocery shopping there because it's rare that I can get out that cheaply. But you're looking at having that range of the lowest amount was $2.32, the most amount was $69.49. Well, trying to look at each one of these pieces of data on its own is not very easy to make sense out of, well, what was kind of the middle amount that was spent and that type of thing. The frequency distribution helps us see patterns a whole lot easier. So if we look at page 48, and I want to take these numbers and make it into a frequency distribution. The first thing you have to do is to determine the number of classes. The number of classes should be somewhere between 5 and 20, and the number you select might be affected by the convenience of using round numbers. So when we're looking at doing this one, probably want to look at doing probably 7 classes. If we look at doing 7 classes out of this, where really we already kind of know what we're going to do as our range of those people that spent less than $10, those people spending between 10 and 19, and that's where we know we're kind of going with this. But taking that kind of thing, so knowing that we have those 7 classes, but using that to kind of think what you're going to do, once I decide how many classes, to figure out the class width, you're going to take the maximum data value minus the minimum data value and divide by the number of classes. So in this example, you'd be taking the 6949 minus the 232 and dividing that answer by 7. And so we'd be looking at having $9.60 in each class if you were to do it exactly. Now, common sense tells us we're not going to start at $2.32 and start counting from there. We also don't necessarily need it to end right at 69.49. We're really wanting to go from 0 to 70. And so if you're taking that 0 to 70, we're wanting $10 to be in each class because we know that that's going to be a nice convenient. We could do $5 in each class and break it up a little bit more, but having those 7 classes is going to give us a visual way, or not a visual, a nice way to kind of organize this data as we're looking at doing it. So now, once we know that, and I'm taking it piece by piece to go through this example so that when you see your own, it kind of helps you think what you want to do. Round this result to get a convenient number. Usually you round up, because if you round it down, then you're going to have more classes than you originally planned. If necessary, change the number of classes so you can use a convenient value. So then choose either the minimum data value or a convenient value below the minimum data value as the first lower class limit. We're going to start at 0. Using the first lower class limit and the class width, list the other lower class limits. We're going to add the class width to the first lower class limit to get the second lower class limit, and so forth. So, okay, I'm trying to remember what I had in here. If we're starting at the 0, we are going to take our 10 and add that on to the lower to get the next lower. You're not adding the 10 to find the upper limit. You're adding 10 to this because these are your class widths to find out what all of your lower class values are going to be. So now we have the lower class limit of our 7 classes. And then list the lower class limits in a vertical column, and then enter the upper class limits. Now, when I'm talking about a class, would it make sense to say 0 through 10 and 1 and 10 to 20 in the next? Let me phrase that differently. What doesn't make sense about that? I'm using 10 twice. Can somebody walk into the store and get $10 worth of stuff? If they do, which one of these do you put it into? You don't know, and it doesn't help us out. So when you're looking at finding that upper class limit, you need to find a value that's below what we have. Now, would it make sense on this one to say 0 to 9? What do we need to put? Okay, we could have somebody come in and spend $9.99. So you have to go with that next lower value that was possible on this one. And so then this would be $10.99. So that we have each of our different classes broke up. And then once we have our classes, take each individual data value and put a tally mark in the appropriate class. Add the tally marks to find the total frequency for each class. So for ours, we don't even have to go with tallying it because it's already in order for us. Most of the time, your data is not going to be this friendly of being in order for us. So for my first class, the one spending between 0 and $9.99, we have 5 values for that. And so my frequency would just be 5. When you go to find between the $10 and $19.99, got a lot more of those. If you were to count that, there's 19 of those data values. And so we can go through and just do our tally as we do. So for ours, these are my classes. My frequency then we had 5 in the first class, 19 in the second, 9 in the next, 9, 3, 1, and 4. So that we total 50 shoppers. Questions there? That is your frequency distribution. Now you can see that, well, the amount that most people at this grocery store that most people bought was between $10 and $10.99. That was the one that was the most frequent value. And so it gives you a visual way or an organized way to kind of see that information a lot easier. Next time, hopefully start today, but finishing it up, next time we'll look at the histogram, which is a way to take this data and to make it into a graph so you can visually see what's going on. But having that organized system makes it a lot easier. Now, if we go back through the different terms that we had. First question, what are my lower class limits? Okay, we found our lower class limits was that first part we had. Those are the ones in blue, the 0, 10, 20, 30, 40, 50, and 60. What are my upper class limits? What's the first upper class limit? Let me ask it that way. Okay, $9.99 would be my first upper class limit. So this one's listing things in your class limits. The other way we could have listed it was our class boundaries. When we talk about finding the class boundary, that's when we have no space in between. That the upper class limit of one becomes the lower class limit of the other. And our definition that we looked at last time, to find those boundaries, it separates the classes so there's no gaps. You take half of the original gap and add that number to the upper class limit and subtract it from the lower class limit. So what is my gap? What's the gap between $9.99 and 10? What's the gap between $9.99 and 10? Okay, it's 1 penny. Well, if we're going to take that and cut it in half, we're looking at a half a penny as that gap. And so you're going to add the half penny to the upper class limits. You're going to subtract the penny, subtract the half penny from your lower class limits. So for my first class, it is going to go from a negative 0.005 to the 995. Again, it's a value you're not physically going to get because that boundary is going to keep it to where everything is obvious where things land. The upper class boundary of that will turn into the lower class boundary of the next class. Because when you subtract half a penny from $10, you're back to the 9.995 to the 10. You guys didn't tell me I was wrong back here. How about that should have been $19.99? That makes more sense. So you're looking at having that range of values. And then doing the same thing for here. We'd be looking at that 19.995 to the 29.995. And we could continue that pattern on. But those are your class boundaries. Again, every single value you get is going to be very obvious, but there is absolutely no gap. And when we graph the histograms, we'll be graphing them using those class boundaries because you're going to have to say, well, where is that line at that's separating my two classes? That line is the class boundary. Because you wouldn't know, well, do you use the line as being the upper class or the lower class limit? It needs to be the class boundary because that is the line that separates things. So there's nobody that's going to be on the line if you're in one class or the other class. Questions there? Okay, the next one we looked at was the class midpoint. To find the class midpoint, you add the lower and upper limits and you divide it by 2. It does not matter if you use the upper and lower class limits or if you use the upper and lower class boundaries, whichever one's given to you. In this case, the limits would be the easiest one to do. And so if I'm trying to find the class midpoint for that first one, you're going to add the lower and the upper and divide that by 2. So you're taking that 0 plus the 9.99, dividing that answer by 2 to get 4.995. If you were doing the second one, you'd be taking that 10 plus the 19.99, taking that answer and dividing it by 2 to get the 14.995. had that 4.995, then 14.995, and that was found by taking that 10 plus the 1999, dividing that by 2. And we'd have that 24.995, and we could keep going with those class midpoints. Questions there? If we wanted to do the class width then, to find the class width, which we created our histogram created our distribution, frequency distribution, using the class width, so we already knew what it was. But if you had the frequency distribution given to you and you're trying to find the class width, you find the difference between 2 consecutive lower limits or 2 consecutive lower boundaries. And it will, again, give you the same answer either way. The difference between 20 and 10 is 10. The difference between 19.995 and 9.995 is 10. So to find that class width, you're just subtracting those different values. So we were taking the 20 minus 10 gave us a class width of 10. Or if we use the last two, 60 minus 50 gave us a class width of 10. There's $10 in each class. So there's that difference of $10 that could fit into that range. Questions on these? And we'll come back and use the same data when we look at graphing the histogram in section 3. And we'll use this one a little bit more as we talk about some other kinds of distributions today. Another one we can use is the relative frequency distribution. It includes the same class limits as a frequency distribution, but the frequency of a class is replaced with relative frequencies, which means it's either a proportion or a percentage frequency, so it's a percent. If it's relative to everything else. It's in comparison to everything else. So to tell me that we had 5 people that spent less than $10 tells me something, but is it 5 people out of 10 customers? Is it 5 people out of 50 customers? Or is it 5 people out of 250 customers? That makes a huge difference. So I need to know how it is in comparison to the rest of the values, how it is in comparison to the total. So one way you can do it is just as a proportion. Well, 5 out of 50 tells me that 1/10 of those values came from spent less than $10. Or we could turn it into a percentage. 5 divided by 50, taking that answer times 100%, would change that into, what did I say? It was 5 out of 50. So we're looking at having 20% of them. We're falling in that category. Or sorry, 5 out of 50 would be 10%. So when we're looking at these, it'd be that relative frequency. Oops, so let's go back and do the relative frequency on this one. I'm just going to squeeze it in over here for the moment. Actually, I'm going to get rid of the midpoints so that I'm just going to get rid of both of these so I can squeeze it in. Chance this works now? So if I was trying to do the relative frequencies instead, relative frequency can either be as a proportion or they can be as a percent. So if I was doing it as a proportion, then I would be looking at having 5 out of the total of 50. Well, 5 out of 50 would reduce down to being 1/10. 1/10 is equivalent to 10%. So you can either write it as a proportion, where it's the 1/10, or you can write it as a percent, as that 10%. If we look at the next one, we had the 19 out of 50. Well, 19 out of 50 does not reduce, but that becomes that 38%. We could look at having the 9 out of 50, which would be the 18%. And this one was the same thing. We could do the 3 out of 50, which is the 6%, 1 out of 50, which is 2%, and 4 out of 50, which we would need to reduce down to being the 2 out of 25, but that is your 8%. Now, if you're doing a relative frequency, these numbers better add to either being 100% of the values, or they better add to being 1 if you're doing it as a fraction. Because you better have every single possibility listed when you are doing these frequency distributions. Questions there? So these are, when you're talking about the relative, it's in relation to the rest of the values. That's a key thing to kind of remember as you're doing these, to know that difference between the frequency distribution compared to the relative frequency distribution. Now, another option could be the cumulative frequency distribution. When you talk about your cumulative GPA, what are we talking about? Okay, it's throughout all of your years. Your cumulative frequency is from the beginning until that point. It's just accumulating as you go. When we talk about things being less than, so if it was less than $10 were spent or less than $20 that was spent, then you're talking about that cumulative frequency. You keep adding. Anybody that spent less than $10 obviously also spent less than $20. And so it just keeps adding up and accumulating as you go. So this accumulates the frequency from the first class to the last class. This is done by adding as you move down through the classes. The last class should be the total samples. Or if we're talking about a cumulative relative frequency distribution, then it'll add up to being 100%. So if we go back to our data and do a cumulative frequency distribution. Actually, yeah, I'll do it right here. So this one's going to totally change. Colors are doing weird things here. We're doing the cumulative frequency distribution. Then my labels are going to be a little different, because then we're saying that we spent less than $10. Well, less than $10 would be that we had 5 of those values. If we went with less than 20, now notice it's less than. 20 is not less than 20. So you're doing less than the next lower class limit. So then if I'm saying we spent less than 20, less than 20 is the 19 people that spent between $10 and $19.99, and it's the 5 people that spent less than $10. So then we're talking about having a total of 24 people. If we're looking at having less than 30, so those ones that spent less than $30 are these other 2 we just had, plus this next 9 people, and so that's a total of 33 values. Questions on what I'm doing? So the less than 40 would be 42 of them. Less than 50 added up to being 45. Less than 60 is just 46 because there's just one more. And then the less than 70 had that total of 50 that we had. So when you're doing that cumulative frequency distribution, this last value you have better be the complete total. If it's not, you have issues. Questions there? We'll be looking at graphing the histograms for each of these different types, the frequency distribution, the relative frequency distribution, the cumulative frequency distributions, and comparing those when we look at section 3.3. Or 2.3, sorry. If we look at example 3, the frequency distribution in table 2.6 summarizes the last digits of the pulse rates of females from table 2.1 on page 7 or page 47. If the pulse rates are measured by counting the number of heartbeats in 1 minute, we expect that the last digits should occur with frequencies that are roughly the same. But what do we notice as we look at those values? So as you look at these heart rates, Is each digit, last digit, getting a chance? All of them happen to be what? They're all even. If they're all even, just from those people, when you've gone to the doctor and you've kind of paid attention to them measuring your heart rate, what's that kind of tell you probably is happening? When you go to the doctor and they're counting your heart rate, so I guess they do it on your wrist, do they sit there for a full minute and count? They usually do what? Either they stay for 30 seconds and they double it, or most of the time actually they stay for about 15 seconds and they multiply it by 4. And so as you look at these digits, it kind of makes more sense that they're definitely not staying for the full minute to get that heart rate. So having a heart rate of 61 beats per minute is impossible for them to measure with the way that they're doing things. Okay, if we look at this next one, Table 2.7. This is randomly selected pennies. So you've got the weights of the pennies in grams, and you've got the frequency. Oops, you can't see what I'm pointing at. What do you notice about this frequency distribution? What seems unusual about this frequency distribution? There's a big gap. You've got weights that are between 2.4 and 2.59 have got a lot of them. Weights between 2.9 and 3.19 have got a lot of them. You don't have any in the middle. Just seeing that part of the distribution, what conclusions could you possibly guess at? What would you think might have happened with the weights of pennies? It got made out of something different, or at least got the proportion of it was changed to where it's no longer the same style of penny. And this is example 4, I think is what it's saying. It's found that pennies made before 1983 are 97% copper and 3% zinc, whereas pennies made after 1983 are 3% copper and 97% zinc. And so they totally flip-flop those proportions. And so you can look at the differences and see, okay, obvious weight change happened. And with such a dramatic weight change difference, there was no values in the middle. But just from this, if you knew a little bit about how much they weighed, you could see which group is before 1983 and which group was after 1983. Okay, if we look at this next one. This is looking at the pulse rates of men and women. In general, what do you think you're noticing? Which ones look like they have a lower pulse rate? It's appearing that men tend to have a lower pulse rate. And so you can kind of just look at this comparison. Now, it's not quite as dramatically obvious of being able to say by the pulse rate, is it a man or is it a woman, as it was with the pennies being before 1983 and after 1983. But we can see that if we're going to compare pulse rates and look at maybe how exercise has changed, exercising so often, how that might have made a change in somebody's pulse rate, well, you're going to have to compare men to men and women to women if you're comparing pulse rates. Because there's a difference between those two, and so that becomes something that you have to kind of look for and pay attention to as you do it. All right, questions there? All right, so that finishes up section 2.2. I want to go ahead and get started on section 2.3, working with the histograms. I know we probably won't get finished with it today, but I'm wanting to be able to at least get done with section 2.4 by Monday also. So, starting histograms. Histograms then are a visual tool to help you analyze the shape of the distribution of the data. A histogram is a graph consisting of bars of equal width drawn adjacent to each other. That means they have to be touching without gaps. The horizontal scale represents the classes of quantitative data values, and the vertical scale represents the frequencies. The heights of the bars then correspond to the frequency values. Histograms look similar to bar graphs with the huge difference that, a couple huge differences. One, they have to be adjacent. They have to be touching each other, and there is not any gap in your values, which means you have to use your class boundaries. Also, when you're dealing with a histogram, it has to be numerical. If you're talking about the different colors of shirts, that is going to be a bar graph because you have different categories, and obviously you can't really say, once you change from a cat to a dog, that there's no in between because that doesn't make any sense. I guess I just changed things, didn't I? Changing from blue to green, that there is no gap between there because there is a lot of variation in colors. And so you can't do that and make any sense. It has to be numerical to talk about making it a histogram. And you have to use those class boundaries because it's without gaps when you do that. The bars on your horizontal scale then are labeled with one of the following. Class boundaries are preferred, where you're listing where the lower class boundary is, where the upper class boundary, not limits, but boundaries are. Sometimes you'll see them listed with class midpoints, especially when you're looking at things that are some different presentations and stuff. Sometimes you'll see the class midpoint listed. The class midpoint, though, makes it more challenging if somebody wants to work backwards and find what was the lower and upper limits. Then the boundary or the midpoints, you actually have to do some work to get to that point. Whereas if you give the boundaries, it's pretty straightforward to find where the midpoint would be. The vertical scale for the histogram, you'll use those class frequencies to be able to do that. Some common mistakes that you see. One common mistake is labeling using your class limits instead of the class boundaries or class midpoints. Again, I like the class boundaries. If you label things on a test where you're using the class limits instead of the class boundaries, you'll lose some points on doing those. Because if you're trying to use limits, do you use the upper limit or do you use the lower limit of the next one? Do you put 19.99 down or do you put 20 down? Neither one. You put the 19.995, that value that's smack dab in the middle that's not physically possible to get. Also, another common mistake is not having a consistent scale. Be sure that any scale is equally spaced and you don't just use the numbers that are provided. This is one of my biggest pet peeves when it comes to graphing. And so if we're doing ours, our scale across the bottom is basically going to be coming from our class boundaries, and so making its own separate scale is not as necessary, as long as when you created your frequency frequency distribution, that every class was of equal width, which is part of the definition of your frequency distribution. But if you start labeling that, well, I've got one class has 3 people, another class has 10 people, the next class has 15 people, another class has 16 people, and you just give me the numbers that you're going to graph, and then you have your different classes that have these different values, then it looks like the space between the changes is staying consistent. Instead of there's a difference of 3 here, a difference of 7, a difference of 5, a difference of 1. And when you look at this, you can't see the change that the difference of 1 should be smaller than the difference of 3, which should be smaller than the difference of 5. You've got to make sure you have a scale that you're counting by. Make your scale first and then graph things afterwards. Because that one, like I said, that is just a huge, huge, huge pet peeve of mine. For good reason. So if we use the same things that we had a little bit ago, so using the grocery information and making our frequency distribution. First of all, what are my boundaries that I need to be graphing? So across my horizontal axis, and my horizontal axis then is going to be talking about the amount spent on the groceries. What numbers am I going to be putting across the bottom? I'm going to do it sideways so that I don't. So we have the negative 0.005 to the 9.995. That next one is going to be going to the 19.995. And so you're using those boundaries that we found earlier. And each of these need to be equally spaced, 49, 59, 69. So make sure that they're not spread out where you're doing, one this far, then the next one closer, and, make sure you have a consistent scale. So those should be the same spacing. For my vertical scale, how high do we need to go? Okay, we need to go above 19, so probably going to at least 20. So what would make sense to count by? What do you say? 1 would work. I don't want to make 20 of them, though. 2s would work. 5s would work, but have some sort of consistent scale that you're counting by. So counting by 2s. Labeling every other one of them. So then you can just make your histogram from there. Where again, each one of those bars will be of equal space. So the first one had 5 of them. The next one had 19 of them. Next one had 9 of them. Next one had 9 of them. Then we went down to 3. 1 and then 4. Having the histogram gives us a way to kind of see what that distribution looks like. Is this a normal bell shaped? Is this one skewed? What kind of graph are we looking at having? And so it gives us an idea of the visual way that it looks. You can obviously see which one happened, which class happened the most often. It gives you a way to visually look at things and be able to compare it. But notice, there is not any space. That when I was graphing this one, when I went to go to do the 9, I started, just tapped into what we already had and went with it from there. Did not need to redraw a second bar graph. You're not, when you're talking about a histogram, if you get something that looks like that with spaces in between, you know you have problems. Because you can't have a space between 19.995 and 19.995. There's not a gap between those. And so that 19.995 is the lower class, or sorry, it's the upper class limit of the second class, but it's the lower class limit of the third class. And so there is no space in between those two things. Questions on that one? Oh, I already had the graph there. That would have made it easier for me to use. I forgot that was there. We'll do relative frequency histograms next time, because I don't want to get in the middle of those and not have time to get finished. So this is just the homework from section 2.2 on here. So do that homework over the weekend. And I know it's rare that I'm letting you guys out again early on another Friday. I don't know how come it keeps ending on Fridays. Not that I'm going to complain about that, but don't plan on it being every Friday that I'm going to let you out early, because it will end soon. The first 3 chapters, it's kind of harder to time things out right, just because it's a lot of definitions and not as many examples to do. I'll be using up the entire time here very soon. Do read ahead. Go ahead and read sections. I should have had you do both of them. Read sections 2.3 and 2.4. So I think this is just 2.3. I should have had both 2.3 and 2.4. So read whatever section 2.4 is. See you guys on Monday. Have a lovely weekend. Correct.